In the first problem, 3 men are pulling to the left and 3 men are pulling to the right. Which direction will the rope move, left or right? And then finally, how much net force will the winning team have?
Alright, my picture is not as good as the diagram on the paper, but it'll suffice. Alright, in the diagram we have 3 men pulling this way and 3 men pulling that way. Under each man it lists the amount of force in newtons that the man is pulling with. So on this side we have 8, 9, and 8. On this side, pulling the other way, we have 9, 8, and 5. So all you have to do is add these up. So 8, 9, and 8 would be 16, and 9 would be what? 25 newtons. And on this side, you would have 17 and 5 is 22 newtons. Okay, so this side would have more force, so the answer to number 1 would be that it's going to move to the left. And you have to be careful because sometimes the net forces will be pushing, as in bumper cars. Now for the second part of the question, how much net force will there be on the winning team? All you have to do is take the 25 newtons and subtract the 22 newtons, which leaves you netting 3 newtons. And it's simply the difference.
In problem number 3, Bertha Butts uses 150 newtons of force to accelerate her car. Her car has a mass of 50 kilograms. How much acceleration will the car have?
Okay, on number 3, Bertha Butts uses 150 newtons of force to accelerate her car. Her car has a mass of 50 kilograms. How much acceleration will the car have? You have to look at your trusty formula sheet. And they are asking for acceleration. The formula for acceleration is force divided by mass. In this case, the force was 150 newtons and the mass was 50 kilograms. When you divide 150 by 50, you get an answer of 3, and then you plug in the correct unit, which is meters per second square.
In the next problem, you explain a contact force and a non-contact force that would be involved with a tennis ball flying over a net.
All right, for a tennis ball flying over a net, this is not a really good drawing, but basically here's a tennis net and there's your tennis ball flying over. As you can see, it has an arc pattern in which it's going to fly because gravity is going to pull it down. You can never go wrong when you select gravity for your non-contact force. It's not touching the ball, but it is pulling it down. So gravity will always be your non-contact force. You can never go wrong with that. Now, for a contact force, something that is touching the ball, air is touching the ball. And as the ball travels, it has to travel through air, and this creates friction. So friction or air resistance would be the contact force.
In the next problem, a man jumped straight up in the air and landed in the same spot that he jumped from. How would potential energy and kinetic energy change during the jump, both on the way up and the way down?
Okay, this is a picture kind of a comic book style, and I forgot his little eyes. Oh, okay. A man jumped straight up in the air and landed in the same spot that he jumped from. how would potential energy and kinetic energy change during the entire jump of the man, going up and coming down? Well, with potential energy, the higher something is, the more potential it has to fall. So as the man goes up and gets to his highest point, that is when he has his most potential energy. So as he goes up, potential energy rises. When he comes down, he loses the potential for more energy because he's getting lower. So as he comes down, his potential energy decreases. So going up, potential increases. Going down, potential decreases. In the case of kinetic energy is movement. So the faster something is moving, the more kinetic energy it has. And everyone knows from common sense and our experiences that when you jump up into the air, the higher you get, the slower you go, until you get to a certain point where you actually stop and then accelerate down. And because you are accelerating, you are speeding up, so your kinetic energy has to increase. But when you go up, your kinetic energy must decrease. So the kinetic and the potential are always going to do exactly the opposite. As you go up, potential increases. Down, potential decreases. Up, kinetic decreases. Down, kinetic increases.